Grade 12 Physics, Special Relativity, Note 4. Length contraction and mass increase. Earlier in this unit, we know that as the speed of light, because it's constant to any frame of reference, it's going to lead to weird results with time, length, and mass. Today we're going to examine the length contraction and the mass increase. So length contraction is governed by this formula, and it's derived a very similar way to the way the time dilation formula was derived. Here L would be the contracted length in meters, L naught would be the rest length, so the time if this thing was just still. V would be the object of the object's velocity, and C would be the speed of light. Again, we can do a unit analysis. Left side would be in meters, right side would be meters times the stuff underneath the square root, but we'll see that that stuff is going to cancel. So left side does equal right side. So what does it mean? Let's use it in an example. Say we have a spaceship moving past Earth at 70% the speed of light, so 0.70 c. If we measure it to be about 78 meters long, so as it's going past the windows, we're looking up and it's about 78 meters long, what would the rest length be? So let's use this new formula to calculate its rest length, L naught. So here L equals L naught times root 1 subtract b squared over c squared. We're going to rearrange that to solve for L naught. So that's what it's going to look like there. Let's insert our numbers. 78 divided by 1 subtract 0.7 c squared over c squared. Now when you expand that square, remember that the exponent of 2 has to be applied to the 0.7 and the c squared, allowing the c's to cancel. Doing the calculation, we get 109 meters. So this means that as objects speed up, their length contracts. Here the rest length was 109 versus the length whenever it was going pretty quick was 78. So to summarize here, as we approach the speed of light, length will approach 0. At slow speeds, let's say we had a cube going by, the cube would look exactly like a cube. But at large speeds, so something near the speed of light, this cube is going to contract, but note this, it's not going to fully shrink, it's only going to contract along the direction of travel. So it's going to look like more of a pancake. The height and the width do not get affected whatsoever. So this is the same if we looked at frames of reference. If a cube was going by, that's what we would see. But if that cube was looking back at Earth, the cube can think that it's at rest, but the Earth is going by at near the speed of light. So first of all, if it was going slow and it saw the Earth go by, there'd be no changes whatsoever. But if that cube was going quick and looked back at Earth, Earth in the same manner will contract along the direction of motion. The height of the Earth would not change at all. So it would look more like a pancake. Only the horizontal direction is contracted. Let's look at mass increase. Mass increase is governed by a very similar equation to the time dilation formula, except we just have masses in this one, and it's derived very similarly. It's actually, we need the time dilation formula to derive this one. Again, m is the increased mass, m naught is the rest mass, both in kilograms, v is the velocity of the object, and c is the speed of light. If we check the units, left side is in kilograms, right side kilograms over the stuff underneath the root, and again that's going to cancel out. So left side equals right side. So here, what does this mean? Okay, let's say we're at the particle accelerator, the LHC in Switzerland. They're going to speed up protons around the circumference of the machine. And the protons are going to reach somewhere around 99.5% the speed of light. What is their increased mass? So we're going to use this formula to see how much heavier they are when they're traveling at 99.5% the speed of light. So we're going to solve for m. So here m, 1.6 times 10 to the negative 27 kilograms on the top. We put that 99.5% speed of light on the bottom. Again, the c squared's canceled. but notice 0.995, it's still, the square is still applied to it. When we do the calculation, we get 1.67 times 10 to the negative 26. So if we compare the two numbers, 1.67 times 10 to the negative 26 is 10 times heavier than the original mass of the protons. So this is only an increased mass in an inertial mass. It's actually a weird effect. There is no actually increase in gravitational mass. The inertial mass, it gives more resistance to acceleration. That's the essence of what mass increase is. Finally, we're going to look at something called twins paradox. Say we have twins, Alice and Bob, they're born, and we're going to stick one on a spaceship, blast it off, and then we're going to keep one here on Earth. Alice is going to go on the spaceship, Bob will stay, and we're going to see what each of them see. So Bob, who stays on Earth, he's going to be on the planet. He sees Alice leave in the spaceship. He waits and waits and waits and waits, and then finally, 20 years later, Alice returns. So Bob is 20 years old, but because Alice left on this spaceship and it was going near the speed of light, she's going to age at a slower pace. Alice might only be 12 years old. So are they still twins if they're at different ages? But the weird thing here is, and what makes it a paradox, is what about Alice? What is she going to see? She gets on the spaceship. She can think that she's at rest and that the Earth is going to go far away from the window. It's going to take a while. The Earth seems to be going near the speed of light, and then Earth comes back. So she might think that Bob is 12 years old. Well, she had to wait 20 years, and she might be 20 years old. Is this possible? So the reason why this is a paradox is because we can ask the question, who's right? Who's 12 and who's 20? Can they both be 12 and 20 years old? This is a neat problem, and this is something that we will examine in class.